The challenge of building a structure weighing hundreds of thousands of tons atop an active rail yard. Hudson Yards realized this through engineering ingenuity and advanced construction techniques. This video explores that journey, from the initial deck construction to the building systems of super tall residential tower, 15 Hudson Yards, and the performance functions of the shed with its movable outer shell. We also shed light on the HVAC systems that pass through these complex structures, and how this project offers a glimpse into a future city where technology and art converge. Beneath the southern edge of the Hudson Yards site runs the Amtrak Tunnel. This tunnel is a critical railway artery connecting New Jersey to Manhattan. Therefore, before constructing the deck above, the Amtrak Tunnel had to be built first. The construction process proceeded as follows. Above the construction site, there were facilities related to railroad operations. The construction began with the demolition of these facilities, followed by full-scale excavation work. Excavation was carried out alongside the installation of a second pile wall. This method involves placing overlapping circular concrete piles in a continuous sequence to prevent ground collapse and groundwater intrusion. First, a guide wall must be constructed. This guide wall helps position the piles within precise tolerances and ensures the required amount of overlap between adjacent piles according to the wall design. Once the guide wall gains sufficient strength, pile installation begins through it. Holes are drilled at regular intervals for the primary piles using specialized equipment. After that, concrete is poured and allowed to cure fully, completing the installation of the primary piles. Then, the remaining sections between the primary piles are excavated. This excavation overlaps part of the existing primary piles so that the secondary piles will interlock with them. Unlike the secondary piles, H-shaped steel beams are inserted into the secondary piles. The moment and tensile forces generated by earth pressure cannot be resisted solely by the concrete for the primary piles, but these forces are compensated for by the H-beams in the secondary piles. Concrete is poured over the H-beams, and once the guide wall is removed, the construction of the second pile wall is completed. After installing the second pile wall, the first stage of excavation is carried out. Typically, soil is excavated down to a depth of 3 to 5 meters, exposing the wall surface for anchor installation. Anchor locations are marked according to the design drawings, and specialized drilling equipment is used to bore holes at an angle of 15 to 30 degrees. High-strength strands are inserted into the drilled holes. At the deeper end, a bone-length zone is formed to firmly anchor the strands into the ground. Then cement grout is injected using a high-pressure pump. This grout bonds the strands to the surrounding soil, enabling them to transfer tensile forces. Once the grout has cured sufficiently, anchor heads and bearing plates are installed, and hydraulic jacks are used to apply the design tension force. After a tieback anchor is successfully installed, excavation continues to a deeper level, and the process is repeated. Multiple layers of tieback anchors are installed to the final excavation depth, ensuring that the entire second wall is stably supported against earth pressure. Next, the tunnel base is leveled in preparation for tunnel construction. Shotcrete is sprayed onto the exposed rock and second wall surfaces for reinforcement. And once the rock is stabilized, a permanent waterproof barrier is installed to prevent groundwater intrusion. Rebar is then placed section by section to form the tunnel walls, and concrete is poured using movable formwork. After the walls are completed, the tunnel liner is installed and rebar is placed for the roof. Finally, concrete is poured and cured, completing the construction of the Amtrak tunnel. For this complex and precise process, the Amtrak tunnel at Hudson Yards was seamlessly integrated as the foundation for deck and future high-rise construction, laying the groundwork for a new city to rise above existing infrastructure. The construction of the Hudson Yards deck began with a direct connection to the bedrock beneath the site. Therefore, the very first structures built were the deep foundations known as caissons. A total of 288 caissons were constructed, each with a diameter of 1.2 to 1.5 meters, and depths reaching up to 24 meters. These caissons were driven down to the bedrock beneath the rail tracks and played a critical role in transferring the structural loads safely to the ground. Caisson construction followed a precise sequence. The first step was casing installation. A drilling rig was used to rotate and drive the steel casing into the ground. The casing supported the borehole and prevented soil collapse during excavation. The next step was excavation. A bucket auger was inserted into the casing to excavate soil or rock to the specified depth. The excavated material was lifted out with the auger as it was withdrawn. Remaining debris and loose material were removed through air surging. Then the rebar cage was inserted. High-strength rebar was assembled into a cylindrical cage according to the design drawings and lowered vertically into the drilled shaft using a crane. However, due to the massive load the deck must support, additional structural steel was inserted inside the rebar cage for reinforcement. Anchor bolts were welded to the top of the reinforcing steel to protrude above the caisson for future connections. The next step was concrete pouring. A special tool called a tremie pipe was used for this process. The tremie pipe was lowered to the bottom of the hole, and concrete was continuously poured as the pipe was slowly raised. Afterward, curing and top finishing of the concrete were carried out. The concrete was cured under controlled temperatures and humidity conditions until it reached the required strengths. The next step was the installation of the cap plate. Once the top of the caisson was leveled, the cap plate, which was pre-welded to the reinforced steel, was connected to the protruding anchor bolts. After that, the steel column to be erected above was connected. The steel columns were hoisted into place using large cranes. The base plate at the bottom of the column was pre-welded and fitted onto anchor bolts protruding from the cap plate, then secured with nuts to complete the connection. A cylindrical formwork was then built around the connection, and concrete was poured to encase and unify the base. Through this process, the foundation and superstructure were fully integrated. Once the caisson foundations were completed, the Hudson Yards deck entered the full-scale superstructure construction phase. These structures were the core of an unprecedented engineering challenge, building a city over active rail lines. Steel columns erected at the top of the caissons were arranged at regular intervals, and trusses and beams were installed to connect them and support the entire deck. In narrow throat zones with dense rail tracks or in long span areas where caissons could not be installed, a 12-foot deep double truss system was used. In some areas, massive steel trusses up to 90 feet long were delivered in segments, hoisted into place by cranes, and connected with bolts or welds between columns or other trusses. Beams were then installed between trusses and columns to form the horizontal framing of the deck. The steel frame connections were not merely temporary. Anchor bolts were tightened to their specified torque values, and high-strength bolts and on-site welding were used in the joints to ensure maximum structural rigidity and integration. Once the steel framing was completed, slab construction began on top of it. Deck plates were installed over the beams to act as both temporary formwork and structural composite members. Rebar was placed on top according to the design, and cast-in-place concrete was poured to complete the floor slab. The deck construction was carried out while trains remained in operation. As a result, scheduling coordination and phased zone-by-zone construction became critical factors. Especially for caisson construction, large equipment such as cranes and drilling rigs had to operate directly above the rail lines. However, a core principle of this project was to proceed without disrupting train service. To achieve this, a rolling outage method was adopted. This approach involved selectively shutting down only certain tracks during off hours, allowing precise excavation and structural work to be performed in that limited window. In addition, deck construction was not conducted all at once, but was instead carried out in phases, from 10 Hudson Yards, the shops, 15 Hudson Yards, and finally 30 Hudson Yards. Some of these zones overlap slightly, And this phased construction strategy was a deliberate decision to optimize scheduling under constraints of ongoing rail operations. In areas where buildings were to rise above the deck, the slabs required high structural strength and stiffness, so concrete was cast in place and cured on top of the installed deck plates. In contrast, areas like plazas and pedestrian zones use pre-cast concrete panels fabricated off-site. This method enabled faster installation in areas with frequent train traffic and minimized service disruption through dry construction techniques. The precast panels were installed using dry joint methods for rapid assembly. Protruding rebar from each panel was inserted into holes in adjacent panels, and concrete was injected through top openings to connect them. And all of this work was carried out using mobile cranes. Due to the operational rail lines below, cranes began their work from the perimeter of the site and gradually moved inward as construction progressed. Once all panel connections and the curing of concrete over the deck plates were completed across all zones, a finishing layer of concrete was poured over the entire surface to complete the deck. Managing the routing of vehicles delivering structural components was also a crucial element of the construction process. Before the deck was installed and while the Amtrak tunnel construction was still underway, materials were transported through a ramp on the east side of the site. This ramp was connected to 10th Avenue and facilitated efficient delivery of components into the site. After the deck was completed, the east ramp was dismantled, and from then on, vehicles delivered structural elements via the area beneath the High Line on West 30th Street to the west. In this way, the Hudson Yards construction team adapted flexibility to changing site conditions at each phase, using strategic logistics planning to successfully carry out a highly complex construction process.
The Shed is opening its doors to the public.
The Shed and 15 Hudson Yards are not simply two separate buildings positioned side by side. The two structures are functionally and organically connected, sharing certain building systems. The Shed's back-of-house spaces, including offices, mechanical rooms, dressing rooms, and storage, are located in the western lower levels of 15 Hudson Yards, especially on the first and basement floors of the residential tower. In addition, many of the mechanical systems required for the performance spaces are integrated into the podium of 15 Hudson Yards. This is a strategic approach aimed at maximizing the artistic and performance space for the Shed. First, the mechanical rooms. Mechanical rooms are located on 4th and 6th floors, with 2 mechanical rooms on each floor. Ducts and pipes connected to these mechanical rooms pass through the 15 Hudson Yards building and are linked to the Shed. However, since the two buildings are connected by an expansion joint, all ducts and piping systems had to be installed with expansion-compatible components. Each system was designed with flexible spacing at the connection point to allow for independent movement. Next is the electrical room. The electrical room is located on the 10th floor of the 15 Hudson Yards building and is connected vertically to the basement levels along the building's core. It is designed to integrate with the overall Hudson Yards microgrid system. Electricity is supplied through the Hudson Yards microgrid, which is connected to New York City's Con Edison power grid. Even in the event of a blackout from the external grid, the system can switch to island mode to supply power independently. Next is the movable structure, the shell. This shell is equipped with ducts and electrical systems, but since the structure itself is mobile, these systems are installed in a detachable form to separate them from the fixed infrastructure.
We start off by disconnecting HVAC ducts and piping. We disconnect 5 services that supply power to the theatrical equipment and mechanical equipment.
This allows users to manually attach or detach the ductwork and electrical connections as needed. This flexible connection system plays a key role in maintaining both the mobility and functionality of the shell. By integrating major building systems into the adjacent structure, the Shed was able to dedicate itself entirely to a programmable space for art and audiences. Hudson Yards presents a new standard for integrated mixed-use development, where architecture, building systems, and the art are seamlessly brought together. The shed offers an optimal environment for both performers and audiences through its spatial flexibility and precisely designed circulation. Visitors enter through the main entrance lobby, located beneath the High Line on West 30th Street. Additionally, the north entrance connects directly to the 34th Street Hudson Yards subway station, providing easy access via public transportation. One of the shed's most iconic architectural features, the guillotine doors, is installed on the north and east facades of the movable shell, allowing access for both people and equipment. When opened, these doors transform the McCourt space into an open-air pavilion, serving as a both passageway between the plaza and the performance hall, and a critical element for adjusting the interior atmosphere depending on the artistic direction. Performers and equipment follow a separate circulation path. Vehicles entering from 11th Avenue can directly access the shed's plaza, while deliveries can be made via 30th Street through the loading dock, which is equipped with 2 truck bays and a large freight elevator. Equipment can be transported to the upper floors via underground parking area and dedicated service elevators in 15 Hudson Yards. The service elevator used by performers and technical crew is also located within 15 Hudson Yards. This efficient circulation planning supports the shed's goal of creating a truly multi-purpose performance environment, enabling rapid stage transitions and smooth audience flow. Hudson Yards is more than just an urban redevelopment project. From the deck structure built over active rail lines, to the integrated systems linking super tall towers and cultural spaces, and the kinetic outer shell that expands performance environments, every element proves the potential of a new city where engineering, architecture, and art converge. Hudson Yards was a vision of the future built atop of existing infrastructure. The traces of that bold challenge still live on. Beneath the rail lines, atop of the aerial trusses, and behind the facade of the shed that welcomes its audience, Hudson Yards is not just about constructing buildings. It is a living experiment that demonstrates how city can evolve, and perhaps a glimpse of the future of urban life. Thank you.